So let's begin with another topic, definite integral. Introduction to definite integral. The definite integral is a mathematical concept used to calculate the area under a curve. It is denoted by the integral symbol and has a lower and the upper limit. The results of a definite integral is a single value representing the total area. You can see in the graph integral how it is. Notation and the limits. The definite integral is written as integral symbol f of x dx from dx from a to b, where f of x is the function being integrated, dx represents the infinitesimal width, and a and b are the lower and the upper limits respectively. The limits of integration determine the range over which the integral is evaluated. The area under a curve is found by evaluated the definite integral over being over the given range. You can see here limit f of x is equal to c, where x raised to a approaching the input of a value on the axis. F of x means function, c is the output value of the function is approaching after substituting the value of a inside the function. Riemann sums. Riemann sums are used to approximate area under a curve by dividing it into smaller rectangles. You can see in the graph the smaller rectangles. The smaller the width of the rectangle, the more accurate the approximation becomes. When the rectangles are in the descending orders at the smaller point, this becomes the accurate. The definite integral provides an exact value by taking the limit of Riemann sums as the width approaching 0. Properties of definite integral. Some of the properties like linearity, additivity, reversing limits. Linearity means the definite integral is linear operator, meaning it satisfies properties like the distributive property and scalar multiplication. Additivity means the integral of a sum of the function is equal to the sum of their individual integrals. Reversing limits. The definite integral with swapped limits is equal to the negative of the original integrals. You can see here the sum of the properties or formulas or examples of definite integrals. Fundamental Theorem of Calculus. The Fundamental Theorem of Calculus establishes a link between differentiation and integration. It states that if f of x is an antiderivative of f of x, then integral symbol f of x dx from a to b is equal to f of b minus f of a. This theorem provides a way to evaluate definite integrals by finding the antiderivative of the integrand. You can see in the theorem, the Fundamental Theorem of Calculus, if f is continuous on a comma b, then the function is f of x is equal to rho x to a f of t dt. Has a derivative at every point x in an a comma b, then it should be like this. Applications of definite integral. Area calculation, volume calculation, accumulation, these are the some of the applications of definite integral. So area calculation means the definite integral can be used to find the area enclosed by a curve and the x-axis. Volume calculation means by rotating a curve around an axis, the definite integral can be used to calculate the volume of the resulting solid. Accumulation. The definite integral can represent the accumulation of a quantity over time, such as total distance traveled or total mass. You can see in the graph a represents the area and that rho represents y is equal to f of x. These are the examples you can evaluate later. Numerical integration methods. When an integral cannot be evaluated analytically, numerical methods can be used for approximation. Some common numerical integration methods include the trapezoidal, Simpson, and the midpoint rules. These methods divide the range into smaller intervals and use specific formulas to estimate the integral. So finally, we come to a conclusion that the definite integral is a powerful tool in calculus for calculating area, volume, and accumulation. It provides exact values of well-behaved functions and approximation for more complex cases. Understanding the properties and applications of the definite integral is essential in various fields of science and engineering. So thank you.